All right, everyone, let's get started. I'm going to do a lecture today. So lab 1 is due on Friday. I think you guys all have it done though, right?
Yep, I just turned mine in.
Cool. So it's still due on Friday. You don't have to demo lab 1, but starting with lab 2, we'll have demos. So I'm going to talk about lab 2 today, but we can't officially start it until next week. We're still waiting on a couple parts for the boards that we're building for it. But I'll talk about it today, and then we'll have 2 weeks to do it. It should be fairly straightforward. Okay, so also we had quiz 1 that was due last week, and we have another quiz that's due this week on Friday. So I just want to go through that real quick. So that we had a question, what's the size of a peripheral's I/O space whose address begins at 1100 in hex and ends at address 2CEF in hex? So for that, you have to just subtract and then add 1. So when you subtract these in hex, you get 1 BEF, and then you have to convert that to decimal and add 7,152 bytes. Okay. Any questions about that? Okay, and the next question is, suppose variable b contains value 1, 2, 3, 4 in hex. To what value will it change after executing the code b equals b, or 1 shifted 5 bits to the left? So basically, we're just setting bit 5 in here. If bit 5 were already set, then it wouldn't change the value. If bit 5 wasn't set, then it will change the value. In this case, it's kind of obnoxious because we have hex. We've got to figure out where bit 5 is in the hex. So bit 5 is going to be in the second hex digit from the right. And so that hex digit is going to cover bits 4, 5, 6, and 7, which means bit 5 is the second bit in this hex digit, right? So that's going to carry a significance of 2 in that digit, right? So in this case, bit 5 or bit 2 within that hex digit is already set because 3 is 1, 1, right? So that won't actually that line of code won't change the value in B. Suppose variable b contains the value 1, 2, 3, 4. To what value will it change after executing the code? This. Okay, now this is what's going on here. So we're taking this sub-expression is setting bit 5, and then we subtract 1, which is going to just set 5 1 bits, right? It's going to create 1, 1, 1, 1, 1, right? And then we're going to take that and shift it 1 bit to the left. So what this is doing is setting a field, a 5-bit field, that's going to go from not from bit 0, but from bit 1 up to 5, right? Or bit 5 down to 1 is going to be turned on, right? Well, in this case, not turned on, but in this case, we're not turning it on. We're not doing an or, we're doing an and. So we're masking off. So what this is doing is it's masking off bits 5 down to 1 in B, right? And by masking off, I mean it's going to turn off all the other bits in B, aside from bits 5 down to 1. Okay, so bits 5, so that's going to span the right 2 hex digits. So the right 2 hex digits are bits 7 down to 0. So bits 5 down to 1 are going to be contained within 7 down to 0, right? Which means the first 2 hex digits for sure are going to be zeroed out. So that 1, 2 are going to be zeroed out. Now, we have 3 and 4. The easiest way to do this would be to convert 3 and 4. Right, that's what I just described. Yeah, so 1 shifted by 5 minus 1 gives you 5 1 bits, and then shifting that 1 bit to the left is going to turn on bits 5 down to 1. So this would be bits 4 down to 0, but by doing a shift, we now have bits 5 down to 1 are masked or turned on. And so, yeah, so like I said, bits 1 and 2 hex digits 1 and 2 on the left are going to get zeroed out. Now 3, 4 is going to be 0, 0, 1, 1, 0, 1, 0, 0, right? Which I don't have that shown there, do I? No. Okay, so 3, 4 is going to be 0, 0, 1, 1, 0, 1, 0, 0, right? So all the 1 bits, let me put an underscore there to separate those two. Okay, so this is the binary representation of 3, 4, and hex. And all of the 1 bits in that binary representation fall within the range of 5 down to 0, right? This is be 5, 4, 3, 2, 1, 0, right? Meaning that by applying this mask, it's not going to change, it's not going to affect any of the bits in the hex digits 3, 4. Make sense? Okay, so what you get, the answer for this is 0, 0, 3, 4. Make sense? Okay. Okay, suppose you want to set bit 3 in the variable b to 0. What line of code will accomplish this? So we want to set b to 0. So, I'm sorry, bit 3 in b to 0. So this line will take, this will set bit 3, and then it will do a bitwise complement. And then, so it'll mask off all, it'll mask off bit 3, in other words, because bit 3 will be set to 0 here. Make sense? So I believe that's, yeah, that's the correct answer, D. Okay. Suppose there's a 32-bit variable named IOStat containing a bit field 4 down to 2 that you want to read. What expression will accomplish this? So there's a couple options here. That some of these are kind of crazy. I try to come up with some crazy ways to do this. So the first option is this one turns off all except bits 4 down to 0. Okay, so the crazy thing here is the order of operations. So this is creating 5 1 bits here. And then the complement is applied to that, so it's going to basically mask off 4 down to 0 in IOStat, and then this shift operation is going to happen last, right? So this masks off 4 bits, the least significant 5 bits rather, and then shifts the whole result 2 bits to the right, based on the fact that the shift is going to happen after the AND, right? Well, yeah, and of course there's parentheses there too, so that's, yeah, that's for sure. Okay. Is that what we want to do? No. No, that's not what we want to do. That's not even the right number of bits, right? 4 down to 2 is 4, 3, 2. That's 3 bits, and this is 5 bits, so that makes no sense. This one is shifting IOStat 27 bits to the left, and then shifting it again 29 bits to the right. Okay, so that's going to take, it's going to shift out 27 bits on the left, right? And then it's going to right justify that 3-bit value all the way back to the right, right? So what we end up with, from the original value, we end up with, let's see, we end up with 32 minus 29, 3 bits. So we only end up with 3 of the original bits, right? And the 27 to the left of that get knocked out, and then the 2 to the right of that get knocked out, right? So what you end up with is the original bit field from the original one would be, let's see, we end up with 0, 1, 2, 3, and 4, right? Yeah, 2, 3, and 4. 4 down to 2, right? So I think that works, right? Right? So basically the idea is that we do the left shift to eliminate all the bits to the left, and then do a right bit to eliminate all the bits that were to the right of that original value. Okay, and then this one shifts 2 bits to the right, and then it masks 1, 1, 1, right? And so that gives us the right answer as well. So actually, I think, sorry, that first one also worked, right? I guess, right? Yeah, because in that case, this retained the 5 bits, the original 5 bits that were on the right, and then we just eliminated 2 of those just to get the 3 that we wanted. So actually, all of these work, right? They all give you the right answer. Right, and then, yeah, and then this one, was this? Yeah, we didn't cover this one yet. So this one took 3 bits and it ANDed it to IO stat after shifting 2 bits to the right. So that also works, right? That gives us the right answer. So all of these give you the same result, right? Yes?
I was going to say, can you go back to A?
Go back to A? Yeah. Yeah, so A was comprised of 2 parts. The first part was we took the low order 5 bits of IO stat and we masked those.
Isn't that a not symbol? Wouldn't that only get the leading bits?
Well, no, because there's the subtract 1 too, right? So you take 1, you shift, you set.
You shift left 5, so you have
So-
1 followed by 5 zeros. Minus 1 is 5, or 5 1s.
5 ones, right? Right.
Not that.
And then this is going to not, right? So this is going to take everything. But oh, you're right. Yeah, that's a good point.
Make it all 0.
Yep, that's right. That's what I forgot about the not. You're right. Yeah, if we took the not off, then we would just have the low order 5 bits, and then we shift by 2 bits to the right, and we get the low order 3. Yeah, that's right. That is correct. So is that, what was the answer? Was the answer all of them, or was the answer all but that one? Was it all? Okay, so that might have been, turns off all except bits 4 down to 0, and shifts the result back by 2 bits. So this would be correct. This is correct, except for this, right? Except for the tilde. If the tilde weren't here, this explanation would be correct. Yeah, so we'll, that's a bug, so I'll have to fix that, right? I think the answer was, I need to check. I think the right answer was all of these, which would be correct if not for that tilde. So yeah, good point, thank you. Which of the following bit sequences shows a pulse width modulated signal with a duty cycle 2 and a period of 5? So I think the first one, right? So you've got a period of 5, meaning that the bit sequence repeats. Every group of 5 bits is repeated, and the duty cycle is 2, which means within that repetition of 5 bits, 2 of them are 1, right? So the answer, I think, is 1. Yeah, because this is a duty cycle of 2 with a period of 1, 2, 3, 4, 5, 6, 7. This one is a duty cycle of 4 out of, is this 4? 1, 2, 3, 4, no, 5. Sorry, this is a 50% duty cycle. This is 10, period of 10, duty cycle of 5. And this is 5 out of 7. Okay, great. Assume a peripheral can raise an interrupt every 20 milliseconds. What's the maximum possible interrupt rate for a CPU configured with an edge-triggered interrupt? I guess it's 50, right? Yeah. Right? How often can you raise the interrupt? 50 interrupts per second. Okay, any questions? Okay, that was good. So last lecture, I was talking about SPI and how do you control multiple slaves with a single SPI master. Well, so one of the limitations of SPI is for sure you can only have one master. There's no way to have more than one master. Generally, you'll also have just one slave, but you can have multiple slaves, but it requires kind of a hack. So the one way you can do it is you can daisy chain, which means you can have, this is the daisy chain one on the right. So you can have one slave select, which activates all of the slaves, and then you daisy chain the bits through all the slaves. So you have MOSI from the master goes into the MOSI of the first slave, and then the MISO of the first slave feeds into the MOSI of the next slave, and so on, until finally you get to the last slave, and the MISO there goes back to the MISO of the master. The problem with this is that the number of cycles it takes to perform each exchange, not transaction, but the exchange, is going to be 8 times the number of slaves. The other approach is to use multiple slave selects. So the master can individually activate one of the slaves. But there's a problem with this. The issue is that all of the slaves are going to have the MOSI signal from the master. So this is a fan out, right? the MOSI comes out of the master and is connected to all the slaves, it branches off, right? But the slaves all have a MISO that they're driving that all gets shorted into the same wire. And so the problem here is that most SPI uses what's called a push-pull interface or a driver interface. So the way that if you have an output on a chip that's push-pull, that output is connected to an inverter inside the chip. And an inverter has two transistors which function as a way to take the output and they call it pull it to VDD, meaning that one of the transistors closes and the other one opens, right? Or vice versa. So you only have one transistor open at a time. There only one is open at a time. If this PMOS is open, then you're basically shorting the wire to the power supply, right? By creating, you're shorting it, but what's really happening is you're creating when this transistor is on, you have a low impedance. It has low on resistance of about 1 ohm or less, right? And then this other transistor then would be off, which would disengage the wire from ground or disconnect the wire from ground effectively, right? Because this transistor, when it's off, is going to have a very high impedance of 1 or 10 mega ohms, right? And then if I want to do the opposite, I can pull this wire down to ground by turning on the NMOS here at the bottom and then turning off the PMOS, which disengages it from the VDD and shorts it to ground, right? So this is basically you're pulling up or pulling down, and then because you have a PMOS and an NMOS that are both shorted, their gates are shorted to the input. This is what guarantees that they're mutually exclusive, because one of these turns on with a 0, as you indicated by the bubble here. You might remember these bubbles from 211. These bubbles indicate active low. And then, in other words, it turns on with a 0. And the other NMOS doesn't have a bubble. The other MOSFET doesn't have a bubble, meaning that it's turned on with a 1. It's active high, right? So because you've got a PMOS and an NMOS that are both using the same gate input, they're guaranteed to be mutually exclusive. Only one can be turned on at a time, right? The problem is that if you have two chips that are using this circuit to drive MISO, master in, slave out, right? The problem is that if they disagree on what they want the bus to be, so now you have two different chips whose output is connected to the same wire. Now, typically this wire is going to be off on the circuit board somewhere. But there's two chips now, and one of them, and this is MISO, one of them is, say, pulling up, right? So this NMOS, this PMOS is on, and the other one is pulling down. This NMOS is on. What ends up happening is they're in conflict, but more important than that, you end up creating a low impedance ground, a low impedance path rather, between the power supply in one chip and the ground in another chip. So what'll end up happening is you'll have current flowing from the power supply in one chip. It's going to come out the MISO wire. Okay, you're going to have this current roaring through MISO, and then it's going to be getting sunk into ground on the other chip, right? And of course, with SPI, it's assumed that they're coupled. They have the same ground, right?
Those transistors will turn into light bulbs really fast.
Yeah, it's going to, like Charles used to say, it's going to release the magic smoke, which means that what ends up happening is you end up sinking more current than they're designed to handle, right? Which is going to cause them to heat. You're going to get heating effects, which could damage them. So for instance, if the on resistance is 1 ohm on both the NMOS and the PMOS, and if this is a 5 volt supply, you basically have 2 ohms. The serial resistance here is 2 ohms. So you're going to have 5 volts over 2 ohms. So you're going to be sinking 2.5 amps through this, right? Which is enough to fry the chip, right? Now, you might say, well, what about these? You can use these things called tri-state buffers. A tri-state buffer is basically what it is it's 2 transistors in parallel, and then one of them has an inverter on the gate, right? Because I remember, like, normally if you have one input going to two transistors of different types, they're going to be mutually exclusive. But if you put an inverter in front of one of the gates, then they'll both turn on, both turn off, right, with the gate input. So that's what this transmission gate is. It's 2 transistors along with an inverter, so 4 transistors in total. And it would allow you to create a buffer in which you have a control input that turns it off, that disconnects it, right? So in principle, you could have 2 mesos. You could have 2 chips that are both driving meso, that both have an output connected to meso on the circuit board. As long as they have tri-state buffers inside those chips, and only one of the chips is allowed to have its tri-state buffer on, which could be done, or one at most, I should say, which would work, right? Because in this case, we have 3 slave selects, right? So the chips would know, they would basically use the slave select to determine whether or not they should turn on their tri-state buffer. So such a thing is possible. I don't think anyone's actually built that, though. I don't think that exists, right? Because SPI is just generally not designed for multi-slave, right? It's usually one master, one slave, right? So if you want to have more than one slave, you're going to use another type of bus that uses something called an open drain. An open drain is where, instead of having a pull down and a pull up transistor inside the driver for each output pin, you just provide the pull down to ground, right? And then somewhere you have a pull up resistor, right? Now the problem with this is that you have to agree, someone has to have this pull up resistor, right? And it's not always clear who's responsible for this, right? But you have to have a pull up resistor somewhere on this wire. It can be inside either one of these chips, or it can be external on the circuit board, right? But what this does is that if both chips that are connected to that wire, if they both turn off their transistors, then they're not actively driving the wire, which means that pull-up resistor will bring the voltage up. Because what ends up happening is you end up creating a voltage divider, because remember, the off resistance of these transistors is about 1 mega ohm. So if you have 2 of these on this wire, the effective resistance of 2 parallel 1 mega ohm resistors is 500 kilo ohms, which is pretty high compared to the 10 kilo ohm that's on the upside, right? So basically you have 10 kilo ohms here connected to a net, and then below that net you have effectively a 500 kilo ohm resistor to ground, which creates a voltage divider which will effectively take that 5 volt voltage and multiply it by 500K divided by 510K, right? So what will end up happening is, if these guys are both off, you'll get a voltage drop here of about 100 millivolts. So this will not be 5 volts, it'll be 4.9 volts, but still pretty good, pretty high enough, right? Right? Make sense? Okay, now the problem is that what happens if I keep adding devices on there, right? As I keep adding devices, the effective resistance is going to drop, right? So obviously I'm limited on how many devices I can add, because as I keep adding devices, the effective resistance of this net down to ground will continue to go down as I add parallel resistors, right? But generally, I don't know what the practical limits are. I've never run into them. But in this case, with 2 devices, for instance, is good. And then if one of these guys turns on, so let's say I turn one of these guys. Oh yeah, and of course the other issue too, by the way, is I will get some leakage current down here. So along with that voltage drop is going to come about 10 microamps of leakage all the time. So this is not as power efficient as a push-pull system. But if I turn one of these guys on, I'll get another voltage divider, except this time on the high side, there'll be 10 kiloohms. And on the low side, I'm going to have an effective, like say the on resistance is 1 ohm here, and the off resistance of this guy is 1 mega ohm. So now I have two parallel resistors. One is 1 ohm and one is 1 mega ohm, right? So, and then I end up with a voltage divider here where on the high side I've got 10 kiloohms. On the low side I have 1 ohm. So this 5 volts now will become 1 over 10k times 5, which is virtually 0, right? So what will end up happening is that I'll be able to pull the net down to 0, right, if I want to zero it, if this guy wants to zero it. And the amount of leakage current I get is now just going to be essentially what's going to come through this 10 kilo ohm resistor and then down through this transistor, right? So the leakage current there is going to be about a half a milliamp, right, through this guy. Which, you know, is kind of high, but the upside of this is that if I decide that I want to have both sides set to 0, transmit as 0, so I turn both of these guys on, right? So say both sides of the connection turn on. Now I have another voltage divider, which is 10 kiloohms on one side and then 2 parallel 1 ohm resistors on the other. Essentially, I get pretty much the same amount of current through there. Well, I get double, basically, right? So I had half a milliamp originally, and now I have another half a milliamp that comes down through the other one. But it's not a big deal. It's not catastrophic, because I'm basically just, now I've got 1 milliamp in total, right? So if in other words, if no one sends a 0, then the default state of the bus is going to be 1. Digitally, it's going to be 1. But it's not really going to be, it's going to be 4.9 volts. There'll be a little bit of a voltage drop, and there'll be some leakage current. But if it's read digitally, the default value of that guy is going to be 1. And then anyone then can set a 0, right? And if I have a conflict where multiple drivers try to pull it low, the amount of current is going to be limited by this pull-up resistor, right? I'm never going to get, in this case, I'm going to get a half a milliamp per device that's pulling down, right? So again, if there's a whole lot of devices, you know, there'll be more, but it'll actually, you know, this ultimately will limit how much current, you know, even, you know, to essentially whatever I drop over a 10 kilo ohm over 5 volts. I'll never go over that amount of current, no matter how many devices pull to 0. Does it make sense? Okay, so what does this all mean? What this means is this is a system that is safe to have multiple drivers attached to the same wire as opposed to push-pull. It's much safer. So this makes it feasible to create a multi-master bus, multi-master channel. Okay, so that's how I2C works. I2C is, I think originally it was called I2C because I2C is an acronym that stands for Inter-Integrated Circuit. And then someone's abbreviated with, instead of the II was replaced by I2. And then some companies like Atmel renamed it again. They called it the two-wire TWC, I think it is, two-wire channel, right? I don't know how they got away with that, but it's the same thing. So the idea is that unlike, so it's a serial bus like SPI, and it's also synchronous. There's a clock. But instead of 4 wires, there's only 2 wires. And they're named SDA and SCL. SDA stands for serial data, and SCL stands for serial clock. And that's fairly, unlike SPI, where sometimes you see different names for the signals, these are fairly consistent, okay? Now, both of these signals are open drain, meaning that they are they both require there to be a pull-up resistor. Again, though, where this resistor is unclear as to who's responsible for this resistor. It could be external or internal. Okay, and then all of the devices you want to put on that bus are connected to both wires, right? And the idea is that any one of these devices can be a master, and anyone can be a slave, right? So remember, with SPI, you could only have one master, and you could have more than one slave potentially if you're willing to hack the bus, right? With I2C, you can always have multiple masters, multiple slaves, so it's much more flexible. Okay, so but the question is, you might look at this and say, wait a second, hold on, where is the slave select? Like, how do we know who's taking the mastership, right? And also, I noticed that there's only one bit line. SPI has 2 bit lines, MOSI and MISO. It's bidirectional. This is not bidirectional. This is a simplex protocol. SPI is a duplex protocol. But like I mentioned to you in class, nobody ever uses the bidirectional nature of SPI. It's never taken advantage of, because generally speaking, when you do an SPI transaction, only MISO or MOSI is being used and the other one's just idle, right? So this makes more sense to just have a unidirectional data wire, right? Make sense? Now that doesn't mean that you can only send data one direction. You can still send data 2 directions, but they'll both directions get multiplexed on that one data wire. So only one at a time, right? Only one host can talk at a time. Okay, so I think I mentioned all that. I2C is multi-master, requires 2 wires instead of 4. Also, I2C is more standardized than SPI. It's more consistent in how it works. There's like a published spec for it, unlike SPI, which is kind of an informal protocol. Okay, so how does the protocol actually work? So there is a transaction protocol that's defined. So it starts out with a start signal, and I'll talk more about that in a minute. It's not a start bit like UART has a start bit. This is not a start bit, it's a start signal. Then there is a 7-bit address. Now there's a 7-bit address is sent by the master. There is an extended version of I2C, I believe, that has a 10-bit address, but we're just going to look at the base version, the original version. It's a 7-bit address. And then there's a read-write flag. Okay, so this part looks kind of like SPI, right? Remember SPI had like a header byte that contained the address and the flag, the read-write flag. But then this is where things get different. There's also an acknowledgement bit. This is something SPI and UART don't have. This one is going to be coming back from the other side of the connection. So if I send the address in the read-write bit, whoever is receiving that is supposed to send an acknowledgement back to me. And if I don't get an acknowledgement, then there's a problem, right? Then I can just assume no one's listening, right? Or maybe there is someone listening, but for whatever reason there's an error. They didn't receive the address correctly, right? Okay, and then the data comes. Now this data could be one direction or the other, depending on if it's a read-write. And then there's another acknowledgement. Whoever received the data is expected to send an acknowledgement back to the sender, and that will depend on whether it was a read or write. Okay, so the problem though is, I mentioned that there's only one data bit, and that data bit is going to be driven by whoever needs to drive it, which means that the master has to send the start and the address and the read-write flag, but then the slave now has to take ownership. It has to take control of the data bit, the data wire, in order to send the acknowledgement. So there's a handover process that's happening. You guys, does it make sense? Like, so I'm controlling the data bit, the data line, as the master, but at some point after, when I expect the slave to take control, I have to release control of it. So there's this handoff, right? And then with the data, it's the same thing where if I'm doing a write, the master will then assume control again after the acknowledge of the data bit to send of the data line to send its word, its byte, and then the slave will have to assume control in order to do the acknowledgement. Make sense? Or if it's a read, the slave will take control after the address, and it will keep control so it can send the data back in response to the read, and then the master will assume control to acknowledge that. Does it make sense? So there's this handoff process, right? Now it's not a really hard handoff process because, as I mentioned, it's using this open drain interface, which someone else taking control is as simple as me just reading the value as opposed to sending a value on it, right? There's nothing really you have to do in order to hand off control. Okay, so the other problem is that acknowledgement adds an extra bit though to each phase. So remember with SPI transactions, it was 8 bits and 8 bits, right? 8 cycles, 8 cycles. Now it's 9 cycles, 9 cycles. Everything is going to be a multiple of 9 cycles always because you always have 8 followed by the acknowledgement. So all of the number of clock pulses will be a multiple of 9 as opposed to with SPI it was a multiple of 8. Okay, so what about the start signal? Okay, so this part gets a little weird. So because it's open drain, if nobody is transmitting, remember that pull-up resistor is going to make the default value of both wires 1, right? So if no one's talking, you're going to have 1 for both, right? Digital 1, right? Logic 1. Okay. When someone wants to talk, they basically pull down one of the wires, right? That's how you take mastership, is you pull down one of the wires to 0, and that's supposed to get everyone's attention, right? That's on the bus, right? Now, the question is which wire and how does that work exactly? So there is a rule with I2C. The rule is that you're never supposed to change the data. When I say change, I mean you're not supposed to change the state of the data wire when the clock is high. You're only supposed to change the data when clock is low, right? The exception to that is when you initiate a start or a stop. The start signal and the stop signal are the exceptions. So the way you initiate a transaction is you've got the clock high, as it is by default, and you pull the data down while the clock is high. Normally, if you were within a transaction, that would be verboten. You would never do that. You'd never change the data when the clock is high. Right? That's a bad thing. But if it's being done as a way to wake everyone up and to take mastership of the bus, then it's okay, right? So basically, the start sequence is I pull data down, right? That gets everyone's attention because they're like, oh, that's not allowed, right? That gets that gives me the bus, and then I pull clock low, right? Make sense? Okay, so then I have mastership. I'm the master. So when you send data, unlike SPI, which is edge triggered, SPI is, remember we talked a lot about how you use CPOL and CFA to figure out what edge of the clock you're reading data. I2C is different. It's not edge activated. I2C uses a level sensitive clock, which means that, so in other words, you guys, hopefully, I don't know if you learned about latches versus flip-flops when you took okay, good, I'm glad to cover that. 211, right. So the difference between a latch and a flip-flop is a flip-flop is edge triggered, meaning that it samples the data on the transition of the clock, right? It uses that as a capture point. Like when the clock is going from low to high, like if it's positive edge triggered, that's when I capture my data. A latch, on the other hand, captures data when the clock is at a certain level, usually high, right? So I2C is a level sensitive. So what happens is that you're supposed to put whatever data you went out on your data line, right? And just like a latch, when you want that data to be sampled by the other side of the connection, you assume it's using a latch to do so, meaning that you raise the clock up, you let the clock be high for a little bit, and then you drop it. And you assume that the aperture time, which is the time that we're reading the data, is not on the edge of the clock, but it's when the clock is high. This is the reason why you're not allowed to change the data when the clock is high. Whoever's sending a bit has to keep data stable throughout the whole time the clock is high. It's very important, right? When that clock is high, don't change anything because it's a latch, and you don't want to change the input to a latch when the clock is high, right? That's the rule of latches, right? So that's what's happening here is that you change your data whenever the clock is low, and then when you want the data to be ingested on the other side, you set clock high, and then you set clock low, right? High, low. And then during the time it's high is when you assume that it's actually reading that data. That's why the start signal is this illegal thing where you change the data when the clock is high, right? That's how you get everyone's attention, is you do something illegal for latches. But during the time you have ownership of the bus, you never change the data when the clock is high, okay? Make sense? Now you might ask, well, how long is the clock supposed to be high for? Unclear. I don't know. Never seen a reference to that. But there's probably some minimal amount of time you're supposed to keep that high, right?
What's a good rule of thumb?
I don't know. On the in lab 2, I have found that 10 microseconds is how high we get high. That was only from trial and error. And that had to do more with the capacitance and how fast the chip could toggle that. I don't think it has to be high very long, though. But it depends on the timing characteristics of the latch they're using to sample it. Okay, so what's happening here? So first thing I do is I get mastership, and then I set my first address. This is most significant to least significant, so I get address bit 6, toggle, address bit 5, toggle, address bit 4, toggle, right? So I toggle it up and down for each address bit. Then I get to the read-write. Now the read-write is a 0 for write and a 1 for read. And then the acknowledgement, so after I send the read-write, so I should say toggle, right? Toggle, toggle, read-write, set read-write, toggle, toggle. Then I sit back and I wait. Well, actually, I don't wait. I toggle the clock again, toggle, toggle. And then when it's high, I'm reading the acknowledgement, right, from the slave, right? Now remember that the default value of the wire is 1. So if there's no slave there, like if the slave dropped off the planet, then when I toggle the clock, I'm obviously going to read a 1 because there was no one on the other side to actively pull the signal down, right? So a 1 on the acknowledgement is what they call a NAC, a not acknowledge. So after I toggle up, toggle down, and I read a 1 on my side, then I can assume that either there was no slave there or something happened and there's no point in continuing this transaction, right, at that point, right? Make sense? Yes?
The slave sending the clock signal, or is it?
No, only the master toggles the clock, up and down. So whoever takes mastership of the bus is responsible for driving the clock throughout the whole transaction, right? The data line, on the other hand, is the one that changes hands throughout the transaction. So if I'm doing a read, the data line, the data wire, the data bit, is going to change control once for the acknowledge, right? And then again for the acknowledge, for the second acknowledge. Because the first acknowledge is the slave, but then it will keep control of the data line to send the data back. And then the master will have to acknowledge, right? So it's master originally, then it goes to slave for the acknowledgement. Then the slave keeps the data bus until the second acknowledge when the master takes control, right? So that's what, twice. Twice you change control of the data, right? The data line. If you're doing a write, on the other hand, it's going to change control 3 times because The master has to send the address. I'm changing control for the acknowledgement. Then I have to go back to master control of data to send the data I'm writing. And then I have to go back to the slave for the acknowledgement. So on a read, the control of the data line is swapped twice, but on a write, it's swapped 3 times, right? Because on a write, you have to swap you have to swap, each acknowledge is a swap of control, and then the data is a swap of control, right? Does it make sense? Okay, so again, though, the master is always control of the clock, and the data is changing hands depending on who needs to talk. Okay. Now, the one thing is, the cool thing about this is setting this high requires that nobody drives the bus. Everyone's transistor has to be off in order for the clock to go high, right? Which means that if I'm a slave and I want to throttle the master a little bit, I want him to, I want him to slow down, cool your jets, right? I can deliberately force that clock down if I want to, even though only the master is supposed to drive the clock, if I wanted to, right? So there is a feature called clock stretching, where the slave can take control. It's not, normal, but if the slave wants to have the master cool its jets a little bit, it can hold the clock low, right? Because anyone can hold it low. It takes everyone cooperating for that to go high because everyone's got to release. But if anyone pulls it down, then the whole bus goes down, the whole wire goes down, right? But I usually don't talk about clock stretching in here. Any questions about that? Okay, so here is my janky waveform graphics again. So if I give you something like this, so notice that our start bit is when SDA suddenly and unexpectedly gets pulled down when clock is high, right? That's our start signal. Oh, and by the way, the stop signal is similar. The stop signal is when, again, the clock is high and data changes, except this time, notice the data is going from low to high. See over here, clock was high and data goes from high to low. That's your start bit. Over here, when you end the transaction, clock was high and data goes from low to high, right? So in both cases, the start and stop bit is when you change data when clock is high. The way that you change data is different, though. In one case, it's pulling it down, and the other one is going up. The other issue is that when you do the stop bit, the clock, remember the clock is normally low when you're not when you're not actively transmitting. So what ends up happening is that in order to issue the stop signal, you first have to bring the clock up in order to get it into the high position. And then you have to change the data. Whereas in the start case, the clock was already high, right? Remember, the default bus it's kind of like in SPI when you have C pull as 1. It's normally high. It's normally high. UART is like that too, normally high. So all I have to do for a start is drop SDA, right? But for the stop signal, the little caveat here is that I have to make sure that I get clock high and then I raise the data, right? So that's the difference between start and stop. So there's my start signal. You'll notice that, again, the data comes down before clock comes down. And then then I have to count 9 plus 9, 18. 9 and 9. 9 bits for the first, 9 bits for the second part. The problem is that I don't know from this waveform who's transmitting. The waveform doesn't tell me who's setting the data, right? I can assume the master is setting the clock, but I don't know if it's the master or slave. In any cycle, I don't know if it's the master or slave that's setting the data. There's no way to really know from reading this, right? Waveforms don't convey that information. So the only way to know is to find the read-write bit. The read-write bit is going to be the ninth the 9th clock cycle, you have to count 9 clock cycles. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry, not 9, 8, not 9th. 9th is the acknowledgement, 8th bit, sorry, 8th cycle. So 1, 2, 3, 4, 5, 6, 7, 8. So the 8th cycle is the least significant bit of like the header field, right? And that's going to be the load, the read-write bit, right? The 9th one is the acknowledgement, right? So the master is sending 1, 1, 1, 1, 0, 1, 1, and then 0. So 0 means write, okay? So now the slave takes control on the 9th bit. That's the acknowledgement, which is a 0. So that's good. And then the next 9 bits are going to be, the next 8 bits are going to be the master, because I'm writing. And then the 9th bit in the second part will be the slave's acknowledgement. Does that make sense? All right, so it's a little easier to read, though, because you don't have to look for edges. You just look, whenever the clock is high, that's when you look at the corresponding value of data. That's how you can decode these. Now, I2C is always most significant bit first for the address and the data. I think with SPI it can be either one, depending on the, what peripheral you're talking to. On the Atmel, on the 328P, there's a way to, I think that's a configuration bit for the SPIs. Most significant bit first, or least significant bit first. But with I2C, this is standardized. Yeah, and I think that's really all there is to know about that. It's always, and then of course the transaction format, the read-write flag is also standardized. It's always the eighth bit from the in the first part of the transaction, right? Okay. Okay, so then here's an example question. What is the stop condition of I2C? So, remember that the stop condition and the start condition have to do with changing the data when clock is high, right? So the rising edge of data when clock is high. The answer is A there, right? That's the stop condition. Okay, so I already described all of this. So SCL is always the master, is always controlled by the master, unless you're doing clock stretching. SDA is controlled by the master and the slave at various phases of the transaction. In a read, the first 8 bits is the master, then bits 9 through 17 is the slave, and bit 18 is the master. Whereas in a write, the first 8 bits are the master, bit 9 is the slave, bits 10 down to 17 are the master, and then bit 18 is the slave. So basically, in a write, the slave only sends an acknowledgement in bits 9 and 18, right? In a read, the slave acknowledges in bit 9 and then keeps control until bit 17, and then the master has to acknowledge in bit 18. Okay? Okay. All right. So how much time do I have? I have a few minutes. So I'm going to talk about, I think this is the last protocol is JTAG, right? Yeah. So I'm going to quickly, this one is pretty short. So the last protocol that we cover is JTAG. JTAG is the way in which the FPGAs are programmed. So it was originally designed as for something called boundary scan. So I have a history of that. No, I don't. So JTAG is designed for testing chips. So the idea is that you connect all of your registers on your chip with a shift register. And then when you JTAG gives you a mechanism by which you can shift bits through all the shift registers on the chip. And so in theory, I could read the entire state of a chip out. And at the same time, I can substitute all the bits that I want to put into the state, right? So it's kind of like SPI works. It's a way to shift all the bits out and shift my own bits in. But because it's a shift register and because there are millions and millions of bits inside, that comprise the state of any modern chip, it's slow, very, very slow. It takes forever. And you might have noticed when you took 313 and when you took 611, When you program the FPGA, it takes like 20 seconds. And you're like, what the hell? It's like megahertz. What's going on here? How can it take that long? It doesn't make any sense. It's because there's just so many bits. It's running at like 1 to 10 megahertz, but there's millions and millions of bits in there, right? So it takes a while. But it's also used for other things now. It's been repurposed a lot. So it's also used for, like on the FPGAs, they piggyback the console on there. They don't do that on the Arduino chips, but on FPGAs they do that. And it's used for debugging, GDB. GDB is a debugger that you can use on the FPGA chips. And to my great anger, you cannot use it on the Arduino chips unless you have an external debugger, right? Although I guess the new ones might have that, right? The RISC-V ones, we think, right? Yeah. Which means, and just so you guys know, we're going to be using the Arduino IDE in this class. I think you have some experience with that from 2.11. There is a button, a very prominent button on the upper left-hand corner that says debug that doesn't work. So what does that mean? It means you can't debug your code. I mean, you can't debug it like a human. You have to debug it like a Neanderthal by printing stuff out. Yeah.
Print the plugin.
Yeah. Or in our case, since we're going to be doing a lot of I/O, we can use the oscilloscope. And so we'll be using the oscilloscope to do some debugging, right? Okay. So anyway, how does JTAG work? Well, JTAG's a pretty neat protocol. The way it works is a single master, multiple slave. And it basically works like the SPI daisy chain approach. The idea is that the master sends data out, and it gets cycled through all the slaves. So you have this thing called test data in, which is basically equivalent to MOSI, right? Test data in goes into the device, and then you have test data out, comes out. That's equivalent to MISO, right? So you basically have MOSI coming in, MISO coming out, except in JTAG it's called TDI and TDO, right? And so the master then shifts all these bits all the way through, and that way the bus is like infinitely scalable. You can add as many things you want on the JTAG chain as you want. Like on the FPGA boards that we use in 313, there's 2 devices on the chain. The FPGA is on there, but there's also a flash chip on there in which you can program a non-volatile memory. You guys ever wonder, like when you turn on the FPGA boards, it starts blinking? And you're like, what is it blinking for? What's going on? That blinking is actually due to the FPGA having been programmed by a flash chip that's on the board. So there's an FPGA bit stream that's programmed into the flash, and you can program that flash too. I always kept that a secret, because if that got out, people could reprogram the flash, and then when you turn the boards on, you can give someone a surprise because it could do something nasty. But both of those devices are on the JTAG chain, and you can add more, right? Some boards have like 10 FPGAs on one JTAG chain. And then there's a clock, so it's synchronous. There's a T clock, TCK, that's fanned out to everybody, and it's driven by the master. But the difference is it has this other thing called TMS, test mode select. And this is the cool part, the test mode select. The test mode select is driven by the master. It's fanned out to all the slaves. And this allows you to put the devices on the chain into a specific mode using only 1 bit. Now, how does that work? It uses a state machine. So what happens is when this state machine has 16 states, I think. 1, 2, 6, 14, yeah, 16 states. JTAG is 16 different states the slaves can be in, the devices under test. And then I can put all of the devices as a master, I can put them in any state I want by sending a bit stream out on the test mode select. And based on that bit stream, they walk through the states based on the pattern of the bits. The way the state machine is set up is that if I put out 5 consecutive cycles of zeros, it's guaranteed to get back to this reset state. So there's no reset input, but if test mode select is 0 for 5 cycles, no matter what state I happen to be in at that time, it will make its way back to the reset state because all these I'm sorry, not 0. It's 1. It's not 0, 1. If I put out 5 cycles of 1, it's guaranteed to get back to this test logic reset. Then, if I put out, say, 0, 1, 0, 0, 1, I'm sorry, if I'm in here and I go 0, 1, 0, 0, I go into the shift data register state, right? And then I keep putting 0 out, and that keeps me in that state, right? And then when I'm in that state, then I use the test the test data in, TDI, to shift bits into the data register, right? And then when I'm done with that, I can get out of there by using test mode select to give it a sequence to get out of there, right? To bring it back to the beginning. There's actually 2 very important states. There's shift instruction register and shift data register. So the instruction register, I go there to put in an instruction, a JTAG instruction, and then I go to the shift data register, and that allows me to send data for whatever that instruction is. The instruction is basically an address, right? So for example, if you guys noticed in 3.13, when you open up the programmer tool, when you open that up, it shows you a graphic of all of the 2 devices on the JTAG chain. You might be wondering, how does it know that? How does it detect that? What it's doing is it goes to the instruction register and sends a special value, which is a device, it's an identification request. It says, identify yourself, slaves. And then it goes to the shift data state, and it shifts all the bits out. And from there, it can tell everything that's on that JTAG chain. So you can plug a bunch of things in the JTAG chain, and you do a scan, a JTAG scan using this approach, and it'll identify, there's a unique identifier for, and then of course you have to have a table of identifier IDs to device numbers, right? You got to know like which, it's like a MAC address. Every ID is this device, right? So every FPGA has its own unique JTAG ID, which is stored in a table, right? Make sense? So it's very similar to daisy chain SPI, except it has this cool test mode select feature. Okay. Yeah, so then, right, so I'll skip over that. Let's see. There's also, I want to point out, there's also a very common protocol called CAN, Controller Area Network, which is it's similar to I2C. It's more complex than I2C. It's got a more complex transaction format, but it's similar to I2C in the sense that it's a 2-wire format. If you understand I2C, you can very easily pick up CAN. And then there's I2S. Stands for, I don't know what that stands for, but it's for digital audio. And so it's like I2C, except there's 2 data lines, one for the left channel, one for the right channel. It's designed for stereo. I don't think it does surround sound, but it does 2 channels, audio channels. Okay, and then I just kind of have a comparison here. I2C half duplex, SPI full duplex, but no one uses it in full duplex. JTAG is, I guess you could call JTAG full duplex because it has in and out, right? Performance, I2C actually has standard performance modes, speed modes. We're going to ignore that in this class, but there's actually specific speeds you're supposed to use for I2C to be compliant, whereas SPI and JTAG there are no published kind of speeds, right? You can run them as just fast as you can, as the technology will allow. And then JTAG, I didn't mention this, but it's push-pull, whereas I2C is open drain. The word size, again, on I2C, there's an 8-bit word size. However, you can have multiple words in a transaction, but each word is 8 bits. And then the addressing is, in I2C, it's fixed. Apparently, there's like a standard set of I2C addresses. It's kind of been standardized for different devices. And I'll talk more about that when I introduce the lab. And then, of course, pins. JTAG is 4 pins, but there are optional pins. You see some JTAGs with more than 4 pins. I can't remember, there's a few optional pins, but there's 4 at a minimum for JTAG. SPI is always 4 pins and I2C is always 2. And then I2C is the only one that has an acknowledgement, although JTAG kind of has an acknowledgement because you can request that it send data back, values back, read registers, in other words. And SPI is like that too, but I2C is the only one that has an acknowledgement that's built into the protocol itself, right? A low-level acknowledgement. Okay, any questions about that? Cool, okay. So let's see, how much time do I have left? I'm just about out, right? I got 8 minutes. I'm going to quickly introduce the next lab. So as I mentioned, we are building our own boards for this class, which is really cool, thanks to Alex. So we built basically it's like a proto board, and we're putting an ESP32, which is an Arduino type chip in there, as well as a speaker and LEDs and accelerometer and headers for motors that we want to use by the end of the class. We're waiting on a couple parts, so we'll have everything fully assembled next week for you. So we're going to be using those boards and the Arduino IDE, which has been installed on all these machines. You tested it, right, Alex?
Yeah,
Okay.
yeah, it works.
Yeah, so one nice thing about that is you guys remember from 3.13 how much trouble you had talking to the FPGA?
Yeah.
Like a lot of times it wouldn't connect. The reason for that is because the FPGAs use this USB blaster type interface. And the way it works is it directly writes in Linux, there's a file called /dev/bus/USB/ the USB controller number / the USB device number. That's a device file. And you just write to that file. And it's not a good way to do it, for whatever reason. Whereas Arduino, on the other hand, it uses the serial USB driver in Linux. So in other words, the FPGAs use a low-level Linux driver for direct writing to USB, whereas Arduino goes through the dev TTY USB driver, essentially, right? That's the difference. So I don't expect, hopefully I'm not surprised, but I don't expect there to be the same level of issues we have programming these boards as we had programming the FPGA boards. Hopefully not, right? The other issue, though, you should be aware of is that the Arduino IDE was secretly converted from a standalone application into an Electron application. Have you ever heard of an Electron? It was done secretly because no one announced it, as far as I know, and they deliberately made the interface so similar to the original standalone application that no rational person would have known anything changed, right? The problem is that they built it on top of VS Code, right? Which is also, so they went Microsoft, right? Which is also an Electron application. And VS Code, when you open it, it downloads gigabytes worth of data into your home directory, but you all have a 2 gigabyte quota in this lab, right? So what ends up happening is you open VS Code and instantly fills your quota. And when your quota is filled, there's no warning, it just fills. And anytime you go to save a source code file, it just zeroes it when your quota is filled, zeroes out your code.
Okay.
So I worked with Ryan about to try to hack it. We hacked it to where when you run it, we trick the software into thinking it's using your home directory when in fact it's using a departmental server directory for all of the board files, right? But it's not well tested yet. So we may run into issues with that. So we have to keep an eye on that, okay? Okay, so what are we going to do with it? So what we want to do is we want to use I2C. We want to program I2C. Now, you don't have to. You could do I2C transactions using the built-in drivers, right? But in order for us to get educational value out of this, we're going to do what's called bit banged I2C. Bit bang means that you use software to implement the protocol. You guys with me? And so I2C is a communication protocol. What are we communicating with? we're going to communicate with an accelerometer. Actually, it's more than an accelerometer. It's a chip that has an accelerometer, a gyroscope, a magnetometer, and a temperature. I don't know why it has a temperature sensor. That's random. But it has a temperature. There's a thermometer in it too.
Put everything on.
Yeah, basically. I have no idea why they did that, but that's just an extra bonus you get. So the accelerometer, we're going to try to use that to measure tilt. So what we want to do is measure the force of gravity, okay, which is going to be distributed along 3 axes, x, y, z, depending on the tilt of the sensor, right? So if you have the tilt, if you have it flat, if it's level with respect to, the floor, right, then you'll see just acceleration in one axis, right, the z-axis, right? It'll be pulling down, and there'll be no accelerations acting on the x and y, right? But then if you tilt it a little bit, you're going to get a little less on z and a little bit on x, but none on y, right? Or if you tilt it the other way, you'll get a little less on z and a little more on y, right? So we want to be able to calculate the tilt angle based on gravity. Now the problem with that is that only works if you're not moving the sensor, right? If you start moving the sensor around, then that fails miserably. So the premise of this idea only works if it's like sitting there, like not moving, not being moved, not being actively moved. Yeah, yeah. Now, if you want to compensate for movement, there's also ways that you can include the gyroscope measurement, but we're not going to do that. Maybe next time. Other people have used the magnetometer to measure tilt because it's basically a compass. You can figure out the magnetic. You can measure the magnetic force along the 3 axes to also measure that. However, if anyone holds a magnet up next to the sensor, then it fails miserably.
I think holding your phone next to it will mess it up.
Yeah, any kind of magnetic field to disrupt it. So all of these approaches have downsides, but that's the goal. Now, but reading it and doing the angle calculation is easy. The hard part is bit banging the I2C. So this is going to be similar to the last lab with SPI, except instead of reading, like interpreting the transactions like we did in the last lab, we're actually going to be implementing the protocol in this lab. Okay, so that's just a preview. I posted the lab sheet if you're curious, at least the current draft of it, up on Blackboard. Feel free to take a look at that. I'll talk more in detail about that on Tuesday, and we'll have the boards by then too. Makes sense? And also, like I said, debugging is going to be challenging because there's no debugger. Basically, the only way to debug this is by printing stuff and by using the oscilloscopes. So we're going to be, you guys have any, are you comfortable with the oscilloscopes? You took, okay, so, okay, oh, and also don't forget to take there's a quiz on like a 7-question quiz on Blackboard. It covers SPI, and then the next quiz will be on I2C. We're lagging behind on the quizzes a little bit, but we'll catch up. All right, thank you.